Okay. The empirical rule. If you look on your formula sheet, this empirical rule is actually on there, and it is written out completely, so you don't have to memorize the empirical rule. It's there. It applies if you have bell-shaped data. So if you see where I'm talking about on the formula sheet, there's like chapter 2, we're in chapter 3. It's the bottom of that first column of chapter 3. It tells us that as long as your data is bell-shaped, 68% of the values will fall within one standard deviation of the mean. So if you know your center and you know your standard deviation, it could be a standard deviation above or below, and 68% of your values fall in that window. 95% fall within 2 standard deviations, and 97% fall within 3. So if we look at this picture, and I apologize, I know that's a little hard to read. I would draw this picture. It's going to be really useful on your homework. I think it's kind of on the bottom of that. Did I print note slide? It's there. You just can't really read it very well. So if you have bell-shaped data like this, you know your mean is the center. If 68% fall within one standard deviation, so that's saying between here and here, that window we have 68%. Now if the mean is the center, if you took that 68% and divided it in half, that means 34% of the values are on each side. Okay, if you want an example, think about if I said the mean was 50 and the standard deviation was 2. And I was looking at a set of values. If it was bell-shaped, that means 68% of those values would fall between 48 and 52. If I just looked between 48 and 50, what percent should I see? 34, because that's one standard deviation below to the middle. Within 2 standard deviations, we have 95%. Okay. We already know 68 of that is in the middle. So if you do 95 minus 68, you get what? 27. And then if you split that up into 2 ends, 27 divided by 2 is 13 and a half. So between each of these windows, we have 13.5%. It said 99.7 falls within 3 standard deviations. So we've already accounted for 95 minus, if you subtract 99.7 and your 95, you get 4.7. Split that up into 2. So that's 2.35% falls in those windows. So if I said what percent of the data is below 54 for this example? Well, how many standard deviations are we away from the middle here? 2. If you subtract, we're 4 away, and a standard deviation is measured by 2. So 4 divided by 2. We're talking about 2 standard deviations above the mean. So it's saying you are right here. And I asked you what percent of our data falls down there. Well, we know up to the center, what percent falls less than the mean? 50, because the mean is the middle. Then if you add your 34 for the first standard deviation there and your 13.5 for the second, we get 27.5? 97.5. Okay. If I said what percent is above 54? Two ways of getting it. You could add up those percents, or we could realize if 97.5% is below, the whole thing is what percent? 100. So 100 minus 97.5 would be 2.5%. Okay. Let's do some examples. So the following represents cholesterol levels of 54 patients. Part A, determine the percentage of all patients that have the cholesterol within 3 standard deviations of the mean according to the empirical rule. So that really has nothing to do with my data, just the empirical rule, what percent has to fall within 3 standard deviations? 99.7. Okay, B, determine the percentage that have their cholesterol between 34 and 69.1 according to the empirical rule. Okay, sometimes it helps people to write out our range of values for each standard deviation. But before I even know that, I need the mean and standard deviation for this data, don't I? How can I easily get that? Calculator. So, what I want you to do, grab your calculator, Chromebook if you don't have a calculator, enter these into your L1. There's 54 of them. Just quickly type them and hit enter. They'll all go in. Remember, you go to Stat, Edit, clear out any values that are already there. I get my mean. Standard deviation, there's an S and there's a sigma. The 54, is that every single female patient? No, so that's a sample, so we need to make sure we're using our S for that. So that would be 11.8058. I'll go to 4 decimal places on this. Okay. So if I'm saying 1 standard deviation, if I want that window of values, you take your mean, the 57.4074, subtract your standard deviation, or to get the highest, you would add your standard deviation to the mean. If I'm looking between 34 and 69.1, the 69.1, that's about 1 standard deviation above. 34, I haven't encompassed that yet. So let's look at the second standard deviation. So you do your mean minus your standard deviation times 2. Or the highest it could be, you add 2 of your standard deviations. So what this is saying is if I'm looking at my data, here's the mean. 69.1 is 1 standard deviation above. 34, that's about 2 standard deviations below. I'm asking you what percent of my people fall in that window by the empirical rule. So if you think about those percents, we know this is the 34, this is the 34. What was this little box? So if you add those together, what do you get? 81 point. 81.5% of my data should fall in that window. C, determine the actual percentage of patients. So it's wanting me to look at the data we actually saw and figuring out how many patients fell between 34 and 69.1. So there are 54 of them. I'm just going to mark off the ones that don't. So smaller than 44 for 34 and bigger than 69. Is that 9 values that I took off? So that means out of my actual patients, there were 54. 45 of them did meet that criteria. So if you want that as a percent, 45 over 54, that's 83.3%. How come it's not exactly 81.5 like we said it should be? Was my original graph perfectly bell-shaped? No. And real life data is rarely going to be perfect, but it was pretty close. We estimated at 81.5 and it was 83.3, so not bad. Questions there? Okay. This one, Chebyshev's works all the time. The empirical rule only works if you're talking about bell-shaped. If it's not bell-shaped, then it says at least 1 minus 1 over k squared times 100% of the observations lie within k. So the empirical rule, I gave you a flat percent. Here it gives you a formula for a percent. This one is not on the formula sheet. That's your copy. If you want to jot it down on there, I would just write it down under the empirical rule. So I would just put Chebyshev's and 1 minus 1 over k squared. And this applies for any set of data. We look at an example. Use Chebyshev's theorem to part A, determine the percentage of patients that have the HDL within 3 standard deviations of the mean. So empirical rule, we can just say 3 standard deviations, it should be 99.7. With Chebyshev's, we actually have to calculate it. So we just do the 1 minus 1 over k is the number of standard deviations. So in this case, my k would be 3 squared. So if we do that, we get 0.8 repeating. So that would be 88.89%. So not quite 89% of our data. Chevy Chef says at least. So we might have more of our data in that window, but we should have at least this much. Determine the actual percentage of patients. So if we look back at that data here, we already calculated the first and second standard deviation. The third standard deviation so if you did your mean minus 3 times the standard deviation, and the mean plus that, it's talking about values between 21.99 and 92.8. If you look at our table, I want to mark off anything smaller than 21.9 or bigger than that. And we don't have any, do we? So what percent of my data fell within that window? 100%. Chevy Chef said at least 88.9% would, and we had all 100. So we got it. Any questions there? Last thing I want to mention is a weighted mean. So a weighted average is found in different scenarios like GPA. You know, if you want to calculate your grade point average and you have, let's say, 3 A's, 2 B's, and 3 C's. Well, in your GPA, an A is worth 4 points, a B is worth 3, and a C is worth 2. So to calculate your GPA, you would have to take your number of A's times the value of an A, which is a 4, plus the number of B's times the value of a B, which is 3, plus the number of C's times the value of a C, which is 2, and then divide by the number of values we had. Well, I had 3 A's, 2 B's, and 3 C's, so how many values did we have? 8. And so you would get your weighted average like that. That's your GPA. Another scenario for a weighted average. Bob goes to a by-the-weight nut store and creates his own bridge mix. He combines 1 pound of raisins, 2 pounds of chocolate-covered peanuts, and 1.5 pounds of cashews. The raisins cost $1.25 per pound, peanuts $3.25 per pound, cashews $5.40 per pound. I want the cost per pound of the mix. So it's like the average. What we have to do is take the cost of the raisins plus the cost of the peanuts plus the cost of cashews and divide it by my total number of pounds. So when I'm looking at this, my raisins, I had 1 pound of those and they cost $1.25 per pound. Peanuts, we have 2 pounds of peanuts, and how much do the peanuts cost? $3.25. plus I have the cost of cashews. So we had 1.5 pounds of cashews, and they cost $5.40. We want to divide by the number of pounds. So we had 1 raisin, 2 chocolate, and 1.5 cashews. So you add those together. And this is money, so 2 decimal places. So I get $3.52 per pound for the mix. Are there questions on any of that? I'd like to just give you the rest of class to work on the homework. So it's what I assigned Friday. Hopefully you watched that video.